Good afternoon, and welcome to Armor of God Apologetics. I'm your host, Wayne Harsha, and I'd like to welcome you today to the third part of our 8-part series on apologetics, and this one is titled The Teleological Argument for God. This is the second one that we're going to be doing in this series of apologetics for Victory Outreach Tacoma. I'm doing this particular video because I noticed that the live stream we did the other day had very poor video quality and didn't really upload very well to YouTube. So I wanted to do this so that you guys could see it a little bit better and so that the sound and video quality would be a little bit better for you. Again, this was a co-broadcasted Zoom and YouTube live apologetics series. And I encourage you to catch the next one next week on the 28th at 6 p.m. Pacific Coast Time, 9 p.m. Eastern Time. So the last time that we met, we talked about inductive arguments. And inductive arguments, unlike a deductive argument where you have at least two premises and the conclusion comes directly from the premises, so that if the two premises, two or more, are true, then it follows that the conclusion must be true. It's like saying, all men are animals, John is a man, therefore John is an animal. Okay, that is a deductive argument. An inductive argument is one based on the accumulation of evidence leading to a probable conclusion. Now, it can be close to a certain conclusion, but technically can't be an absolute conclusion. It's only a probable conclusion. And another way to put this is, it is an inference to the best explanation. And two examples include the the minimal facts argument for the resurrection of Jesus by Mike Licona and Gary Habermas. The other would be the one we are going to deal with today, which is the teleological argument for God's existence. Now, recall from our previous two discussions that all beliefs begin with a claim. And in this case, our claim is that God exists, that the triune God of the Bible exists. And so following that, you then need to give reasons for your belief or your claim. And in this case, we call those theistic arguments or arguments for the existence of God. Now, last week we discussed the cosmological argument, which comes from the origin of the universe itself. And we talked about how there are two different types of cosmological arguments. The first is one that is an atemporal argument, meaning one without time, and that's the one by Aquinas and Leibniz, and how it fits very nicely with Genesis 1:1, in the beginning God created the heavens and the earth. And then we talked in quite a lot of detail about the cosmological argument for God's existence, which is a very simple and eloquent deductive argument that states whatever begins to exist has a cause. The universe began to exist, and we back that up by a lot of scientific evidence, and therefore the universe has a cause. But this week we are going to be dealing with the teleological argument for God's existence, and this comes from the Greek word telos, which means goal or purpose. But in modern times, we oftentimes refer to this as the argument from design. Now, I would actually try to persuade you that it's not one argument, but actually multiple arguments from design. And we're going to go over these in quite a lot of details. Now, that being said, I do want you to understand that in reality, these are very wide-reaching, overarching, and very, at times, technical and specific details about the argument from design. So there's no way I can cover all of that today. But again, I just want to equip you with some of the main evidence for God's existence. Now, the teleological argument actually goes everywhere from the argument of the fine-tuning of the universe to the fine-tuning of our planet for life to the fine-tuning of life itself. And in this case, you can even see at the bottom how DNA comes into that, and we'll talk a lot about that. And we'll talk about how that even goes down to the smallest of life forms in bacteria, and in fact even at the cellular level with the concept of irreducible complexity, which one of which is the machine called the bacterial flagellum, and we'll talk about that in quite a lot of detail toward the end of this session. Now, I'd like to start with this quote, and it is from Fred Hoyle, and it says, "A common sense interpretation of the facts suggests that a super intellect has monkeyed with physics as well as chemistry and biology, and that there are no blind forces worth speaking about in nature." It should be noted, by the way, that Hoyle was in fact an agnostic for quite some time, and that this realization is one of the things that led him to at least theism, if not deism. So let's start by talking about the absolute fine-tuning of the universe as a whole that indicates that it had a designer. And we'll start by talking about just 4 of the fundamental forces present in the universe. One of them is very obvious to us on a daily basis, and that is gravity. The others maybe not so much. But those are the electromagnetic force, the strong nuclear force, and the weak nuclear force. So let's just take a few of these and talk about how extraordinarily fine-tuned each of these constants is in nature. The first is the ratio of gravity to the electromagnetic force. And I will tell you that if it were changed by simply 1 part in 10 to the 40th power, there would be no large or small stars at all. In other words, the universe as we know it, our sun as we know it, even our galaxy as we know it would not exist. Now, to give you an example of, or just a picture rather, of what 1 part in 10 to the 40th power looks like, that's this number written out in zeros, and you can see that's an incredible amount of zeros there. But to give you a little bit better graphic understanding of this, if we took the entire North American continent and we put silver dollars, coins, a quarter or silver dollar, and we stacked silver dollars, not just 1 deep on all of the North American continent, but we actually started stacking them, kind of like you see here, but in equal stacks. And we painted one of those red, and we stuck it in one of the stacks, and we began taking all of those stacks all the way to the moon. If we took our friend Susie and we put a blindfold on her and asked her to pluck out the red coin, the chance of her doing that would be 1 part in 10 to the 40th power. So you can see how extraordinarily large this number actually is. Okay, it's immense. It's beyond our understanding, actually, how big that number is. But that's not the only one. Let's just isolate gravity for a moment. Now, the capital G is the nomenclature for the gravitational constant. That's not what our gravity is here on Earth, but the universal gravitational constant throughout the entire universe in our solar system. It's seen here. Now, this number is not really important in and of itself, okay? What is important is how finely tuned that number actually is. So let's look at it this way. If the gravitational constant were changed by just 1 part in 10 to the 60th power, life wouldn't exist at all. The universe would not be life-sustaining with anything resembling what we think of as life, okay? Now, to understand how big that number is, our human body only contains about 10 to the 14th power cells. Our entire human body, okay? 10 to the 14th, how many cells our body has? 1 part in 10 to the 60th power is how much you would have to alter gravity and not get life, okay? So 1 part in 10 to the 60th power is that many zeros. That's an extraordinary amount of zeros. And again, if that gravity were any different, things wouldn't look anything like we see it now, because either the universe would have imploded on itself if gravity were stronger, or if the gravitational constant were weaker, it would have just dispersed into everything and we would have never gotten the formation of galaxies or stars. So let's look at another thing that has to do with that, and you can see here in this equation, which is the equation for the expansion of the universe, not only the capital G, but you see this lambda. Now, lambda is the cosmological constant, and the cosmological constant is one of the other kind of fundamental constants in our universe. And if we changed the cosmological constant by just 1 part in 10 to the 120th power, the universe would not exist at all. It just simply wouldn't exist as we know it. Okay? Put another way, Stephen Hawking, the world-famous late physicist, said, if the rate of expansion of 1 second after the Big Bang had been smaller by even 1 part in 100,000 million, that's 10 to the 120th power, the universe would have collapsed before it ever reached its current size. So you can see now, you're starting to see how extraordinarily fine-tuned the universe and the universe's constants, like gravity and cosmological constant, are fine-tuned. Put another way, Lee Smolin, another theoretical physicist, said, perhaps before going further, we should ask how probable is it that a universe created by randomly choosing the parameters would even contain stars? The answer in round numbers comes to about 1 chance in 10 to the 229th power. That's 1 part in 10 to the 229th power. I don't even think there's a name for how big that number is. It's huge. It's extraordinarily large. To put it another way, take you back to chemistry class way back in high school or middle school. Remember, there are 3 things in every atom in the universe. That is protons, electrons, and neutrons. If we took all of the protons in the entire universe, all of them, and we made each one of those protons its own individual universe with different properties, none of them statistically would contain stars. That is how extraordinarily fine-tuned our universe is to simply exist. So that hopefully now is giving you an understanding of just how extraordinarily designed and technical and precise our universe is. In fact, Paul Davies, another world-known astrophysicist out of Arizona State University, said, the cliche that life is balanced on a knife edge is a staggering understatement in this case. No knife in the universe could have an edge that fine. So let's think about this. If we look at fine-tuning, what are the possible explanations for fine-tuning? Well, could be due to necessity. In other words, it just has to be that way. And in fact, some atheists would say that's the case. It just has to be that way, otherwise it wouldn't exist, and if it didn't exist, we wouldn't be here. But I reject that argument because, for me, it's not out of necessity. The universe theoretically could have existed in some other way, and therefore it's not necessary that it is present in the current way. The other option is chance. And then the third thing is design. Well, let's think about necessity. Again, like I said, necessity doesn't hold. While it is necessary that the universe is as finely tuned as it is for us to observe it, it does not hold that the universe is necessarily existent as it is. In other words, the gravitational constant, for instance, could have been slightly smaller and the universe could exist, but simply not in the current form or fashion. The other thing is the universe could exist in a form or fashion that holds it together in some way, but yet not be a life-sustaining universe. So the other possibility is chance, and I just talked to you about what are the chances of the universe existing exactly like it does. And some would say, well, so you're telling me there's still a chance? Well, theoretically, yes, but one chance in 10 to the 229th power, no one would in any other circumstance say that that is a chance that's worth even discussing. So in my mind, the fact that the universe came into existence out of chance, finely tuned exactly like it simply does not hold. The other question then is, well, what about design? Well, since it's not the result of chance or necessity, therefore the data are a result of design. Therefore, there's a designer. You can't have a design without a designer, in the same way that we talked last week about the fact that you can't have a building without a builder. You can't have a painting without a painter. You cannot have a design without an intelligent designer. So let's talk about the privileged planet of Earth, the only life-sustaining planet that we know of. Why do I call it the privileged planet? Well, because of this book. It's an excellent book I would recommend called The Privileged Planet by Guillermo Gonzalez and Jay Richards. And in fact, in the description for this, I will have linked Jay Richards' video regarding the privileged planets. Well worth your while to watch it. So it turns out that there's a reason they call it the privileged planet, and that is because there are so many factors that have to go into the Earth itself to make it a life-sustaining planet. First and foremost, what you see pictured there is the Milky Way galaxy. It is a spiral galaxy. Well, it turns out you need a spiral galaxy or a planet in a spiral galaxy in order to potentially sustain life, and it just so happens the Milky Way is in fact one of those spiral galaxies. But not only that, within a galaxy there are the spiral arms, and then there are the spaces between the spiral arms, and it turns out that you actually need to be located within the space between the spiral arms. If you're in the spiral arm, there's just too much in the way of cosmic radiation and bombardment and things of that sort. It won't sustain life, and it just so happens, as you see in the picture here, that our planet is in between two of these spiral arms. Now, the other thing that you need is you need a star that is just right. It can't be too large. If it's too large, the planet would be too hot to sustain life. If it is too small, the planet would be too cold to sustain life. If it's too hot, you don't have enough liquid water, and you need liquid water for life. If it's too cold, you also don't have enough liquid water. Again, liquid water is necessary for life. You also need the planet to not be, the sun to not be too young. If it is too young, it burns too hot, and it gives off too many large elements, and that would bombard our planet with too much radiation and keep it from being a life-sustaining planet. It also can't be too old. If it's too old, as we talked about last week, because of the second law of thermodynamics, it will have burned out too much of its energy, and the planet would be too cold to sustain life. And it turns out our sun is not too big, not too small, not too hot, not too cold. Just like Goldilocks, it's in the perfect spot. It's in the perfect measurements we need it to be. Furthermore, our solar system and where we are in the solar system is extraordinarily important. Number one, as you know, we're the third rock from the sun, and we need to be in that kind of excellent zone right there in order, again, not to be too hot if we're too close or too cold if we're too far away. But in addition to that, the other planets in our solar system are actually extremely important as well, and especially Jupiter and Saturn. Not only are they important because their size and gravitational pull keeps us in the correct orbit around the sun, but more importantly, because the size of those planets has such great gravity and such great size that it actually helps us from bombardment from too much debris in space, too many asteroids or meteorites, and that helps keep our planet protected. Now, it turns out even our moon and so many things about our moon are super important for us. Number one, the size of our moon, if you look at it compared to the size of our planet, our moon is actually very large. And that solves really three problems for us. Number one, it keeps us on the correct axis tilt. If we weren't on that axis tilt and we were more straight up, there would be more extreme temperature differences and variations. That's a problem for us. Number two, if we weren't on that correct tilt, and more specifically, if it didn't hold us on that correct tilt, then our planet would start to wobble in its rotation. And then, of course, the third thing is that the moon is very important to us in terms of our tides. And again, we've talked several times now about how important the water is on our planet for sustaining life. What about the gravity of the Earth? Now, I'm not talking about the gravitational constant we talked about earlier. I'm talking about the gravity on the Earth. It turns out gravity on different planets is different, partly because of what is made up in the core. And the gravity on our planet is so extraordinarily fine-tuned that if it were changed by 1 part in 10,000 billion, our planet wouldn't sustain any life. And that's very important for us, obviously, and you can tell that's extremely fine-tuned. So let's talk a little bit about the fine-tuning of life itself. Now, when we talk about the fine-tuning of life, in order to do that, we really need to start with the origin of life. How did life come to be on this planet? Of course, Genesis 1 talks about how life came to this planet, but let's talk about kind of a little more of the specifics of that. First of all, naturalists, materialists who believe that everything came from evolution usually believe also in what's called abiogenesis, which is that amino acids began to form proteins, which ultimately began to form one-cell organisms, more complex organisms, which ultimately evolved into humans. Frank Turek likes to call it from the goo to you via the zoo. But let's look at some of the evidence for that versus the evidence that the hand of God is what created life. Now, in order to do that, let's talk about what is life, because if we don't define what life is, it's going to be really hard to talk about what actually was the origin of life. So some would have you believe that amino acids are not necessarily life, but are really, really close to life. And I'd like to actually show you that I don't think that's the case, and I don't think science really backs that up. So let's look at what is probably the simplest functioning life itself on the planet, and that is the mycoplasma bacteria. Some might argue that viruses are the simplest life, but I would actually say that they're not, because viruses require a host in order to replicate. And so to me, in order to have life, you have to have the ability to replicate, and mycoplasma is a single-cell bacteria that has the ability to replicate. Now, if you look here, the life of mycoplasma bacteria isn't just amino acids. Instead, it's a 3-layer cell membrane. There are soluble proteins, not just amino acids, but fully formed and functioning proteins. There's cytoplasm, there is soluble RNA, ribonucleic acid, there's DNA, and then there are ribosomes, which are basically a certain type of functioning protein. And so you can see that amino acids alone are not life. Now, here's why a lot of atheists and materialists will kind of go to amino acids as being the building block of life. It has to do with an experiment about 66 years ago called the Miller-Urey experiment. And basically what these two scientists did was it was what's called origin of life science, and they were trying to actually create life. And so in a test tube. Okay, so what they did was they took a soup of what they considered was probably the chemicals that were there in the early Earth and early Earth atmosphere, and they heated it, and then they put a spark in it, and lo and behold, they got some amino acids. They got some simple ones, as you can see here. Some of the amino acids are much more complex. Others are kind of more simple. The ones that Miller and Urey got were actually quite simple amino acids. But the problem is that experiment has been debunked many, many, many times, and no one has ever actually repeated it, and certainly no one has even come close to actually creating life in a test tube. By the way, even if they did, you got to stop and think about that. If people in a lab create life in a test tube, that's actually evidence for intelligent design, not natural processes. But nevertheless, the reason it was been debunked, they didn't use the correct atmosphere. The other thing is that they used very highly concentrated and very pure chemicals, unlikely to have been the case in any kind of natural chemical reaction. So let's look a little bit more into the cell and a couple of processes within the cell, and we're going to talk about transcription and translation, which means going from DNA to RNA and then RNA to a protein. Now, in its simplistic form, basically in order to form a protein, DNA gets transcribed from DNA into RNA, and then RNA gets translated into a protein. But what you see there as kind of a simple line of amino acids linked together to make a protein is not really accurate. When it's first being made, it is that the amino acids individually get linked like that, but then they start folding and turning on each other. And it turns out that folding is actually a 3D structure is very important for its that protein's function. And so initially it folds into a secondary structure, and then a tertiary, and then a quaternary structure. And many of these proteins don't actually take on their function until they've reached their full mature quaternary structure. And so it turns out if any of those things go wrong, the protein doesn't function properly. So let's look at one more detail of that. So you see here, it's that same diagram I used earlier, but it adds two things in there. So to go from DNA to RNA, you need this thing called an RNA polymerase. And then in order to then translate that RNA into a protein structure, you need, and by the way, polypeptide means protein, you need a ribosome. But the question is, what is RNA polymerase? Well, it turns out it's a protein. So let me get this straight. You need a protein in order to transcribe DNA to RNA in order to get a protein. Hopefully you're starting to see the problem. The next thing is, what's a ribosome? That's the thing that takes RNA and makes the protein out of it. Well, it turns out ribosomes are actually an organelle, meaning a substructure within a cell that's composed of proteins and RNA. So you need a protein with an RNA in it in order to take an RNA to a protein. Again, here's the problem. You need all of those, but they all need to be together at the same time. And if you look at just the replication of DNA, it's even more complicated because it needs all of these things like topoisomerase and helicase and primase and ligase. It also needs an RNA primer. Now, what are topoisomerase and helicase and primase and ligase? Well, they're enzymes. What are enzymes? Enzymes are proteins. So again, you need proteins and RNA in order to even replicate DNA. But how do you get RNA? DNA. How do you get proteins? DNA and RNA. So you see, the problem here is that in order to replicate DNA, you need RNA. You also need proteins. But in order to get RNA, you need DNA. And in order to get RNA, you need proteins, but you also need RNA in order to get proteins. So what this is an irreducibly complex system. All of those things, DNA, RNA, and proteins, all need to be present fully functional in the same place, in the same time, in order to get the processes of the cell that we call life. So it's an irreducibly complex system, meaning that if you take away one of those parts, the cell doesn't function, it doesn't live, there is no life. So now you can see the intertwining of those three things and how complex that is. Dr. James Tour, who's a nanoscientist who talks quite a bit about origin of life sciences, says molecules do not care about life. Nobody has ever seen molecules assemble towards life. Molecules do not move toward life. Nothing has changed in origin of life science in the last 66 years. His video is linked in the description below, and I hope you check it out because it's actually a really well done discussion of origin of life science and how there's just essentially no way that chance and molecular processes alone are what results in life. Michael Behe, who I'll talk about a little bit more later, says that in private, many scientists admit that science has no explanation for the beginning of life. Darwin never imagined the exquisitely profound complexity that exists even at the most basic levels of life. You see, you need to understand that in Darwin's time, when he was talking about evolution, the cell was as small as they knew. And according to them, all they knew about the cell was it was just kind of a blob of protoplasm. They didn't know anything about organelles within the cell. They didn't know about DNA. They didn't know about the nucleus. They didn't know about any of this kind of stuff. And that just goes to show you how things have progressed since Darwin's time. So let's talk a little bit about DNA, and let's talk specifically about the language of DNA. Now, language has two things in common. The first is, all language, that is, has two things in common. The first is the transmission of information, like the Rosetta Stone. The Rosetta Stone transmitted the information that allowed us to translate ancient Egyptian hieroglyphics. Prior to that, we had no way to do that. So the question then is, does DNA transmit information? And the answer is absolutely. First of all, I will tell you DNA is actually the same structure in a one-cell amoeba or in a human body. Now, some atheists will say, well, that's indication that that DNA is what is behind evolutionary biology. I would submit to you that, well, maybe it's actually that design is so exquisitely perfect that God used it for all life and all formation of life. Now, you know, the interesting thing is that DNA actually contains, even the amount of DNA in a one-cell amoeba contains as much information as 1,000 volumes of the Encyclopedia Britannica, and the amount of DNA in a human cell contains the same amount of information as 8,000 volumes of the Encyclopedia Britannica. So you need to understand, if you take just one human cell and you were to be able to splice out the DNA and lay it end to end, it would actually stretch for almost a meter. It's extraordinary the amount of information contained within DNA. Look at it this way: DNA is simply a four-letter code. It's kind of like Morse code. You know, in Morse code, there's only three things, right? Dots, dashes, and spaces. In DNA, there's four. There's C, T, A, and G. And the arrangement of that is what gives it its information. It's interesting, actually. For a long time, it was thought that DNA actually contained a lot of quote-unquote nonsense or non-useful or just blank DNA. But it turns out, actually, as we learn more and more and more about DNA, it turns out a lot of those spaces that we thought were nonsense DNA are important in starting and stopping proteins from being transcribed and translated, and in other signal processing. So what kind of information does this DNA put forth? Well, actually, it puts forth a lot of information. It puts forth, consider this, every cell in your body contains all of the information needed for the differentiation of every single type of cell in your body. It's not like the cells in the nerves are different, the DNA is different than the cells in your muscles. No. In fact, your muscles contain all of the information in it for the differentiation of nerve cells, muscle cells, fat cells, bone cells, blood cells. So it contains all that information, all that signal processing. Remember, it all comes from one fused cell, one sperm and one egg fuses. One cell becomes our entire body. So all that information is contained in every single nucleus of our body. It also contains a huge amount of information on cellular processing, what kind of proteins. Again, the proteins made in muscles is different than the proteins in nerves. And it contains all the information not only about how to replicate, how to divide, but when to divide and when to go through programmed cell death called apoptosis. So it's an extraordinarily huge amount of information. The other thing that all language has in common is that it's produced by an intelligent design. Frank Turek likes to use the analogy of alphabet's cereal. Some people use alphabet's soup. And he says, if Travis were coming downstairs and he saw his favorite cereal, alphabet cereal, and on the table it was spelled out, Travis, take out the trash. And he even uses Travis, take out the trash, Mom. No one in their right mind would think that someone just spilled the alphabet's box and Travis, take out the trash, Mom, was spelled out. That it's insane to think that. Well, it's also insane, for instance, to think if I'm walking down the street and I see a flyer about a party tonight or a concert tonight, let's say, down at Town Hall, my favorite band at 7 p.m. on the day I happen to be walking down the street. No one would ever think that the ink on that page just magically appeared. The ink on that page was put there by an intelligent designer. Take it one step further. Shakespeare's tragedies, you're walking down that same street, you pick up a book that you see laying on the sidewalk, and it's actually Shakespeare's tragedies of Macbeth, Othello, King Lear, and Hamlet. Now, even semi-intelligent beings like 1,000 monkeys with 1,000 computers and 1,000 years would never type a single page of a Shakespeare novel. It takes a certain type of intelligence to get that amount of complexity and specific information. It takes a designer to give you a design. It takes an intelligent mind to transmit information in language. So the question is DNA produced by intelligent design? Well, I'll give you this quote by Bill Gates. DNA is like a computer program, but far, far more advanced than any software ever created. No one would ever think that software was just happened. It's always created by an intelligent creator. DNA is a complex, a computer program far more complex than anything Bill Gates has ever seen. So in an analogous fashion, a Windows computer and those programs implies Bill Gates. The language and information in DNA implies an intelligent creator, God. At least in my mind, I think so, wouldn't you? So that has led to a book by Stephen Meyer, who actually lives in Seattle, called Signature in the Cell, the DNA Evidence for Intelligent Design. That book in the Amazon bookstore is linked in the description below. I encourage you to check it out. And then the last thing we'll talk about is actually at the subcellular level, and that is a concept called irreducible complexity. Biochemist Michael Behe in 1996, and a few years before that, started looking at the biochemical things in life that he started noticing a pattern that it didn't really fit with evolutionary biology. You need to understand what neo-Darwinian evolution holds. It holds that to get from one species to the next, what actually happens is gradual, unguided, small changes happen, and those changes lead to an advantage, some sort of survival advantage or food advantage, and they get kept in a certain population. The population that doesn't have it dies off. That's the whole survival of the fittest. And then that change, ultimately, there's another change that gives them another advantage. So you have to have this small stepwise change that ultimately leads to a new formation, a new cell, something that causes a life advantage for that organism. So Behe started noticing that there are things in nature that don't fit with that. And he termed that irreducible complexity. And he uses the example of a mousetrap. Now, a mousetrap only has 5 parts, okay? A base, a catch, a hammer, a spring, and a holding bar. Pretty simple. But if you want to build a mousetrap, you better have all of those parts at the same place, at the same time, and fully functional in order to get a mousetrap to act like a mousetrap. Now, if even one of those things, like a catch, is either missing altogether or only partially functional, you don't get an effective mousetrap. In fact, you don't get a mousetrap at all. You just get a paperweight. Okay? So that's what irreducible complexity is. Even more complex than that would be the example of a watch. You see all those little sprockets there. Well, it turns out in a self-winding watch, you need all of those springs and sprockets to be in place, working, fully functional at the same time. You can't stepwise build it. In fact, as a watchmaker stepwise builds a watch, the watch doesn't function until all the parts are in place and functional at the same time. So Behe uses the example of the bacterial flagellum. It is said to be the most efficient motor ever invented. And in fact, this motor is so incredible that it can turn at 100,000 RPMs and then in 1/4 turn stop, reverse direction, and start going 100,000 RPMs in the other direction to change the complete course of the bacterium that it is propelling. It's used to propel bacteria through like water in order to get toward a fuel source like sugar. And it has all these parts, bushings and rotors and inner membranes, outer membranes, the hook, the filament, the stator. You need all those things. And as it turns out, if you take away even one part, it doesn't just not function well, it doesn't function at all. And what does that tell you? Well, you couldn't have stepwise gotten to that and gotten any function, because again, it's not that it just doesn't function really well. Like, it's not like if you took away the hook that, it rotates, but only at, 50 revolutions per minute. No, it doesn't work at all. So it all has to be fully functional parts, fit together, same place, same time in order to function at all. That's irreducible complexity. Another example of that is the human eye, but even more importantly is a lot of the biochemical pathways in the human body. And as it turns out, there are a lot of disease processes and syndromes that result in either extraordinarily shortened lives or no lives at all if there's any error, inborn error of metabolism in one of these very complex systems. So it turns out some people will say, oh, well, the bacterial flagellum irreducible complexity thing by Behe has been debunked. No, it hasn't, first of all. But second of all, even if you debunk one thing that was thought to be irreducibly complex, that doesn't debunk irreducible complexity. It only debunks that one thing. And so you would have to debunk everything that is considered currently irreducibly complex in order to debunk the concept as a whole. So what is the inference to the best explanation of the fine-tuning of the universe and our planet and life? What's the inference to the best explanation? Here's my inference to the best explanation. Psalm 19, 1 and 2 says, "The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge." And Romans 1, 19 and 20, which states, "For what can be known about God is plain to them, because God has shown it to them. For his invisible attributes, namely his eternal power and divine nature, have been clearly perceived ever since the creation of the world in the things that have been made, so they are without excuse." I hope that answered more questions than it brought up, and I hope this has blessed you. If you liked what you saw today, please sure to get with us next week on the 28th, where we will be going over the moral argument for God's existence, which I find one of the most compelling. That's every Tuesday night for the next 5 weeks. and it's can be found on this page of Armor of God Apologetics YouTube, as well as our Facebook page, and the Victory Outreach Tacoma Facebook page. You can find the details there as well. I hope to see you then. I hope this message really helped you out and blessed you. We hope that you enjoyed the content of our video today. If you did, make sure to give us a thumbs up and share this content. Also, don't forget to hit the subscribe button and hit the bell so that you are alerted to any new content that we post on our channel. Please remember that all of our video content is completely free of charge and can be reposted, shared, and embedded. You can also find us on Facebook at facebook.com/armorofgodapologetics with an S. Thank you for watching and have a blessed day.
And you are worthy of it all our worship, Jesus, for from you are all things, and to you